Hello everyone and welcome. Oh, look at that big flashing lights up in the corner there. So it changed the camera angle a little bit. We've got a view there of our board that we are developing code developing code for. And as you can see at the moment, it's just got one section of the LEDs is just running a little bit of a pulsating pattern just to test it out. And it looks really, I guess because the room's a bit darker, it looks very bright, but how are we all doing? Today I wanted to basically start working on the firmware for all of these knobs. So just look at me, reach back into the other side of the screen here. Each of these little silver things is what's called a rotary. Probably couldn't hear me because I wasn't on the mic. Each of those little silver things is a rotary encoder. And a rotary encoder is very similar to, you might have heard the term potentiometer or a pot. Basically a knob or a dial, but there's a critical difference between the two. A potentiometer has a fixed low and high point, right? They're the dials that you can turn on so far and they just stop, and then turn so far the other way and they stop. That's a potentiometer. It's a simple mechanical thing. It's a simple mechanical resistor, basically, with a high point, a low point, and what's called a wiper that sort of moves between those 2 points. And the wiper, determines how much resistance it's getting by where it is on that scale of high to low. Pretty simple. Hey Tony, welcome. For this synth build, though, I wanted to go next level of interesting, which is we're using rotary encoders. And rotary encoders, they spin continuously, right? There is no fixed high and low. Because one of the things that I hate about traditional synths and musical instruments is the notion of like you load a preset or a patch, and the front panel that you're looking at doesn't reflect the patch you've just loaded. Like, let's say for example you've got 4 knobs on a synth, and you load a preset and knob 1's at position 2, but the preset might have loaded saying that knob should actually be at position 10. But it doesn't work that way, and then you have all sorts of janky behavior where sometimes as soon as you touch that knob, it'll jump from what looks like the value of 2 where it is right up to 10, because that's what the patch says. Or sometimes you've got to sweep it up to 10 to find the 10 and then start moving it. And it just, I find it really, really frustrating. So we're going to do things differently. We're using rotary encoders for this, so that there is no, the knob itself doesn't communicate what the setting is, but instead the lighting around it, the LEDs around on the board will reflect, can't talk straight, will reflect what the actual value is of that knob or that dial. And you'll see more of what I mean about that soon enough. And so let's just flip to our schematic here. This control board is a giant thing, and I went a bit nuts with it in terms of there is something like, I think there's 41 rotary encoders, so 41 knobs, dials, whatever you want to call them, whatever suits best and doesn't make you giggle. There's 41 or so of these, and they're grouped by 4s, and each group of 4 is controlled by one programmable integrated circuit, or a PIC. And the PIC is this lovely little chip created by Microchip Technologies, and it's essentially a little programmable CPU. You can write code, you can upload the code to it, and it does what it does. The reason I chose these is because it has these things in them called CLCs, customizable logic cells, which allow you to set up a couple of little simple gates that understand the way in which these encoders work. Now, the theory of how these encoders work is really quite tricky. Whereas a potentiometer is simple, right? Remember, it's just that wiper moving between the high and low points of resistance. A rotary encoder is very different. Inside a rotary encoder, actually, let's see if we can get a little image here that'll help make sense far more than my hand wavy sort of images will. Rotary encoder quadrature. Let's just see. Excuse me. Just seeing if we can get like an example of the insides. Yeah, look, this little. This, there we go. Yeah, that looks like it's a good one. Inside a rotary encoder is this little spinning disc, right? And so it spins like this, and it has like often patches where there is a metal conductor, right? There's basically patches that are on and off, on and off, on and off around in that circle, right? So think of it as a disk where there's just little slices of on, off, on, off, on, off, on, off around the disk, which means when you spin that disk, the little output terminals on it, there's three terminals actually. There's a common or a ground, and then there's an A terminal and a B terminal. But as you spin that around and those little slices of contact material come into contact with the pins, it creates a pulse wave, right? And you can sort of see this being illustrated here. As that disk spins around, the terminals will start to see, oh, I've hit the contact material, and oh, no contact material. Oh no, I've hit the contact material, right? Because it's spinning around and getting in contact with those terminals. The magic of a the magic of a rotary encoder is that they produce a quadrature signal, which means it's two square waves, two square waves that are 90 degrees out of phase, right? What the hell does that mean? It means that if you're turning the disk one way, you think about that disk spinning around, the contact material is going to hit one of the terminals faster than it's going to hit, or sooner than it's going to hit the other terminal. But then when you spin it the other way, because that's coming back around the other way, the other terminal will see that contact material first before the other one, right? So that's how you determine whether you're turning clockwise or counter. I love my word talk ability in bed this morning. That's how you determine whether you're spinning clockwise or counterclockwise on a quadrature encoder. And then it's just a matter of counting the pulses to determine how far has the user turned that knob. So yeah, that's what we're going to write the code for today. And we're going to do this in MP Lab. IPE? MP. I've used MP Lab before on natively on the Mac, but I'm having a lot of trouble with the performance of these Java-based IDEs running directly on the Mac. So I'm switching back to my Linux development environment. This is going to be a wall of pain. Let's not do this in Linux. Let's just keep doing it in the Mac. We've got our STM development environment working well on Linux, but we'll stick to doing our microchip PIC programming on the Mac. And so the PIC is this thing that will read those signals off the rotary encoder and basically keep track of what knobs and dials are being turned and how far, and report that back. That's what I think we want to work on today. Now, I don't need that to show up every time. Now, I think all we've done so far on this PIC is just set up the basics of the board. Let's make this, that is our primary already. Let's just check out our config. That's the actual PIC there. You can see it there. And so there's 4 of the rotary encoders attached to it. This one might only have 2. It can also do a couple of other ancillary functions. You can have a number of LEDs attached to it, like we use RC0 and RC1 as LEDs here. And that just allows us to, like for example, one of these rotary encoders has a push button switch built into it, so when you press it, these LEDs will change to indicate, in this case, whether you are affecting the volume of the square wave, or if you've pushed it and are turning it, then you're affecting the pulse width modulation of the square wave. I'm having all sorts of trouble today. So one thing I did want to try and do, I just want to take a quick look at everywhere that we're using LEDs on this. Looks like that's the most. We're using LEDs all on RC0, RC1, RC2, RC3. Has that got any LEDs off of it? Yeah, no, RC0 as well. No LEDs off that guy, no LEDs on there. This one has 2 and it's on RC0, none there. Oh, this one's got 4 and they're all, oh no, hang on. Yep, that's got 4 and they're all on ports RC0, 1, 2, 3, 2 on that one, none on that one. Awesome. The reason I was checking that was because I think at the moment we've got RC0, 1, 2, and 3 set up to just be general purpose I/O pins, which means we can basically turn an LED on or off. But I want us to do something better than that. The other really nice thing about these, the particular pick that I chose here, is that it has a pulse width modulation LED sort of driver thingy, for lack of a better way to put it, built into it. It's basically, it's able to generate its own pulse width modulated signals. I'm going to add that in. I'm going to try this out. Let's do PWM3. So enable PWM, select a timer, timer 2, polarity active high. That all looks good. Now what we could do here is go down to RC0 and set that to PWM3 output. Haha, nice. And then I think from memory, there was also a way to do this thing called the CCP, comparator. Let's just add these. I think this was a way to extend pulse width modulation to a few more pins. Let's see, can we change this one now? CCP1 output. Yeah, I think that's how we do it. So we'll add both the PWMs. Oh, not DSM. PWM, where are you? There you are. Okay, add that in. Right, so the first two LEDs will do PWM3. This one will be PWM4. And then for the other two LEDs, we'll add in the CCP. I can't quite remember what the difference is between the CCPs and the PWM. But in terms of wanting to generate just basically a variable voltage to drive an LED, they should be very comparable, I think, or at least that's what my testing led me to believe. So we're going to set that up like that. Alrighty. Otherwise, we've got everything else set up to basically be determining these quadrature signal encoders. We've got CLC 0 and 1, CLC 4 and 5, CLC 2 and 3, 6 and 7, which should match essentially what we do down here. Which is, we have rotary encoder 1A, 1B, 3A, 3B, 2A, 2B, 4A, 4B. Yeah, that makes sense. Okay, let's generate that code. Generate. Configuration has warnings. Oh. What's the warnings? How do we... Oh. Please configure timer 2 for PWM mode. Okay. Makes sense. Ah, yeah, that's right. I remember now how the CCP works. So it takes you configure a timer that's basically just a part of the chip that's always oscillating at a particular frequency. And then the CCP will do sort of its own comparison on top of that to generate sub-frequencies off that timer. Hopefully that makes sense. So we're going to enable this timer. We're going to set it to the high frequency internal oscillator, which means it's going to be oscillating at 32.7 kilohertz. That seems a little bit slow. Why is that so slow? High frequency internal oscillator. Okay, we'll leave it for now. Oh, hang on. Configure timer 2 to off. Hang on. Right. Timer 2 is used by PWM3, so we need to set that first of all to free oscillating over 4. Okay. I'm getting there. So if PWM uses timer 2, PWM4... PWM3 uses timer 2, PWM4 uses timer 2. Post-scaler settings in timer 2 does not affect calculate parameters. Okay. So let's turn them off then. So PWM3 Uses timer 2. Where's this? Post scaler setting does not affect calculator. Okay. Well, I don't care. I don't care. Do you care? I don't care. Well, let's just ignore that. What's this category here? This like... Obviously these are bad. Let's just try generating the code and see what that does. Or maybe... Maybe we should set that to use a different timer. You know what, let's just do it. Let's try generating the config, see what this does. We can always come back and work this out. Well, that seemed okay. mClear pin cannot be disabled when low voltage programming is enabled. We don't want low voltage programming. How do I turn that off? System module. Turn low programming off. Okay, now, haha, here we go. Current system clock is a high frequency internal oscillator. High frequency internal clock is 4 megahertz. PLL capable. Okay, fine. Alright, now I think we're good. What we should now be able to do is... Oh, what's happened here? We lost our video feed? I seem to have frozen on the Twitch. Oh, nope, I'm back. Apparently. Quality shows it pretty low though. What's going on here? Alrighty, well, folks, let me know if we're having trouble with the video again. But I think we're good. I think we just generated our config here. What we need to now do is plug our programmer into one of these chips. The question is, we need to find one that's going to be a good example. I want one that's running all 4 encoders and all 4 LEDs. This would be a good one. Where's that? U16. Let's click on that. Find it in the schematic. Oh, there it is. U16. Is that you? Click it and go back to the schematic and make sure that's it. Yeah, U16. Okay, so we're going to attach our programmer to that chip, which is the one directly above that interconnect board there. Okay. All right. Well, bear with me a second, folks, and I'm going to just jump off camera and go do that. Back in a second. You can watch me on the board cam up there. Hold up. All right, so hey Cyrus, nice to see you there, and Brian, welcome to you both. Okay, so we just plugged in our PIC programmer. Let's just see if it can actually see the chip. Because I'm not sure if you can quite see it there on the board cam, but I had to make my own little custom cable for the PIC programmer because I chose 1.27mm pin pitch for the header, and the pinouts are all weird, so I had to make my own. Uh-oh, kid's come out with a kid update. Hello, kid.
Morning tea?
Yes, it is morning tea time. Well, it's close. All right, yes, go, have it. Forgot to turn the board on. There it goes. Okay, board's now powered up. As you can see, the green lights are on. Let's try that again. Let's just try... Oops. Oh, I clicked the wrong button. I don't know what that button's going to do. What's that going to do? That's going to read it. Alright, well either way, it's found the chip and it can talk to it, so that's the main thing. Yes, Keyblade. Thank you. Yes, okay. Kid's got this dance that... I don't know, it stresses me out. Alrighty, so, oh jeez. Cool, alright, so folks, we're cooking with gas here. We've got our programmer hooked up. It is able to talk to the chip. That's awesome, it sees it, yes, okay. Let's make it do something. So now that we've got all the configuration set up, let's just close all this. Close, 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 close. All right, let's make it do something. Where's our source? Where's our main? Here it is. So we've got a while one loop here. Let's just see if we can actually make those LEDs do something. Oh yeah, well, that worked, didn't it? That definitely worked. But we don't need to make the LEDs do anything because they're already just turned themselves on. You know what, I wonder if we can do this without actually doing any code, because I think you can, in the initialization here, actually change the duty cycle, which should make these LEDs dim. Let's see. Now, interesting, I'm just trying to look at which LEDs it's actually turned on. Okay, cool, it has turned on all four. And those are positioned around those rotary encoders so that we can tell which one of those is actually in use. Or what the setting is, I should say. That didn't make a lot of sense, did it? Okay, so what do we got here? Where did... I've lost something I need here. System module. Oh whoa, I've lost a little little tab that I need up here. I'm not sure where that's going, but that's all right. We'll try doing it a different way. Let's see. Can we go to this pin? Just affect its config? No. Alright, let's try this a different way. Let's click on that, and then let's reinitialize the configuration thing. Ah, there we go. So now we've got resource management up. Let's change this. So that's interesting. So it's... well, I don't know why. With a duty cycle of 0, we've got LEDs turned on. But let's run this code and see what happens. See if any of those LEDs change. So there we go, they're turned off. Now, is one dimmer than the other? I can't tell. So let's configure the other one to have a duty cycle of 1%. And then go down to our pulse width modulation. Now that's interesting. That's got a 50% duty cycle. So I can understand why those were lit up. Let's run this code now, just see if we see any difference in those red LEDs. Do they get a little more dim? No, I can't really notice a change in them. So that's interesting. So with a duty cycle of 1% and a CCP at 1%, 20%. What's going on here? Maybe we need to check the pins. See what we're doing here. So CCP is configured for analog, it's configured for output. There should be no pull-up or anything else. No, that looks good to me. Likewise, analog and output. Okay, so why is... Oh, you're a clown. You're going to generate the config first. Of course there's no change. Okay, now that we've generated the actual code, there's a little bit of a difference in the way, yeah, see, there we go. I saw some warnings about this. So let's see, now the LEDs change. They went off. Well, now they all look the exact same brightness. Yeah, no. Looking at them on the board, and there's, they all look full bright. So, what do we do? So the timer's running. PWM3. Timer is timer 2. Ah. Software control. I just want to make sure this is always running. Clock sync? No, I don't think so. We definitely don't want a timer interrupt. Yeah, I had some test code written for this on a breadboard with this PIC, and I wish I could find it, but I cannot. And the only thing I did find is some sampler code for a very similar project that I looked at a while back. So let's just see if we can open this up. Let's see if we can just choose a project. What? No, that's a new project. That's not what I want. Open a project. That's what I want. Because maybe this will just give us a little bit of a reminder as to what we got to do here to set our PWM LV set digital input. No, that's the switch. Hey, Wooly Bully, how you doing, man? Sorry to see your tweets over the last couple of days. I hope you're holding up all right. Okay, RGB encoder mode. This. Right, so they use CCPs for this. Okay. Yeah, man, sounds like it has been rough, but I hope you're doing all right. All right, so how do we set this CCP value? And why do all my LEDs come on? Oh, nice. Final interviews at our table today. So Mr. Willy Bully's been interviewing around a bunch of places. Well, fingers crossed, all things crossed, man. I hope you get some good news there. Fade GP1. I wonder if that might tell us something. GP1, update out GP1. Config, RGB encoder mode. Fade GP3. PWM GP3 LED. Okay. Where's that? There we go. Right. Okay. So it's just setting the registers into the CCP. Well, it's not doing much that we're not doing. Let's try some different values here, and let's just monkey around with this. Let's set a duty cycle of 80. And I wonder if we should just to keep things safe, because you know, I get nervous about these things. I'm gonna actually just turn this off for the moment. How do I clear the pin? Can I not do that? Alright, well, we'll just set this as GPIO output. Actually, you know what, to be totally safe, I'm going to set this as a GPIO input. And input. And I'm only just going to set up one of these LEDs as CCP1. And then, so that means in the resources here, we're going to take out our PWM. Take out our PWM4. We're only going to have CCP1 enabled. And it's using timer 2 as its settings. But we haven't... Oh yeah, we do have timer 2 in here. I'm going to close timer 2. And that's going to say, Turner, we need timer 2. Okay, so we'll add timer 2 back in with the default configuration, and it's going to say, in order to use PWM mode, please configure timer 2 to use FreeOSC over 4 or FOSC over 4 as the clock source. Okay. There we go. So now I'm going to set this to a duty cycle of 50%, generate the code, upload it to the board, and just see. And hopefully we just have one LED on at that point. That's good to hear, Mr. Woolly Bully. I really do hope it goes well for you. And of course, keep us up to date. We all want to hear the updates. Alright, that looks like config is generated. Let's run it on the board. Run it on the chip. How cool is this? We're writing code that goes and gets uploaded into a little chip. That still just blows me away. Except something broke. Let's just try a clean. Then we'll try a build. Oh, did it work that time, did it? There we go. Magic. If it doesn't work, stop and start. What's happening? Aha! One little light. Nice. Okay. Now let's see if we can configure the brightness of this. So let's go to 90% duty cycle. You know what? Let's be grown-ups now, and let's do this in code rather than monkeying around with the thing. So what we need to do is we need to take a look at the MCC generated files, and there'll be one in here called CPC. And there should be one. See all the CLCs. Where's the CCP? No? There's a PWM1? Okay, it is, because that's... right. So we ought to just be able to... Well, how do I set... Initialized duty value is 511. How handy. So the initialization works like this, and it's setting... Where does it set that initial value? I don't see that used anywhere. How strange. That's a bit weird, isn't it? Must be some other code somewhere. Find in projects. Okay, it's defined in PWM. But then never used. What? Now that seems a little weird to me. But maybe that's part of the problem, right? Now if we look back at this other example code that we had here, it sets the PWM I see. It's got like a PWM 5 duty cycle high, duty cycle low, so these must be right. So we need to find what is that value, or where is that parameter in our set of code here. Maybe up in the headers here, MCC generator files, pwm.h, pwm initialize, output status. Well confused. I've missed a step. That's the overriding feeling I get, is I've missed a step. Is this right? Enable CCP. CCP mode pulse width modulation. I don't want an interrupt. Or do I have to adjust the timer? No. Where's this coming from? I wish I could find the code that I'd already written for this long ago. This is weird. Unless it's just like a value that exists, like magic. Come on. PWM5 DCH DCL. Look, let's just try it, right? Do we have something similar in our configuration? In our PWM1, see, we've got a RH and RL mode, PWM enabled, format right aligned. Their configuration is set the PWM options to be selected, blah, 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 blah. Yeah, so this is a different, well, it's not that different a model of the chip. I don't know why this would be so different. Let's have a look at their configuration. Maybe that will help us make some sense of this. And this is not really the area that I thought we'd be focusing on today, but it's just a little distraction, so we shouldn't get bogged down in this for too long, folks. Otherwise we'll regret it. Let's just turn off MCC. Do you want to say, sure. And now open this one up, which is the example file. Or maybe I've got to make that the active. No? Why not? Nope, oh, it is. It's just taking its sweet time. Right. How have they got this configured? Well, they're running at a really high. They're running at a much higher internal clock, which is interesting. But more importantly, let's check out their config. So they're using the CLCs just like we are to talk to the rotary encoder, to interpret the rotary encoder. But yeah, look, see, this is different. They've added a PWM5. That's why it looked different to us. But they do use these CCP 1, 2s, and 3s. RC5, left, right, because they do. This board is designed to do lots of different things, but I really. It's this one here, this PWM left. I think it's pulse width modulation LED red GP3. So pin 2. If we look at the CCPs, they're actually not configured within the outputs. PWM5 is configured with outputs. What? Oh, they must reconfigure this in code. Okay, well, that's not going to work for us. Okay, let's just try and make sense of the other stuff in here. So the CCPs are all in there, and they're all in pulse width modulation. Okay. And then there is a PWM5, which is created and has timer 2 as its source. These all use timer 2 as its source, so that looks promising. Timer 2 is there. It's enabled. And it has prescale or postscale, the same settings as we've got. And that seems to be running. Okay, so why don't we try something a little bit different here? Or actually, hang on. So we know PWM5 is actually a real PWM peripheral, but the CCPs, how do they use those? Because I know that's a different way to achieve the same end. PWM GP1. No, it's all touching pulse width modulation green LED. Update the pulse width modulation to the green LED. Yeah. And it does this by setting CCP R2. Right. And if we try and find where CCP R2 is, get set. Okay. Oh, my nose is itchy. Okay, so these are just right. Okay. All right. Okay. It's making sense to me. It's making some sense to me. Let's close all our files before I get file claustrophobia. Turn off the configuration. No, don't save it. And now what I'm going to do is I'm going to go back to our firmware project here, and I'm time boxing myself of only spending a little bit more time on this before we actually get into the rotary encoders, because getting the LEDs to work is not what we should be doing right now. But it's fun. So we'll set this as the main project, and I think what we need to do is go into our configuration. Here we go. And I opened a lot of stuff. I'm going to enable two things. So we've got CCP1, but I'm also going to go and enable one of the PWMs just to have a comparison of configuration modes, see which one's making sense. So I'm going to add PWM3, which is pulse width modulation, basically a way to generate a variable voltage. So pulse width modulation is enabled. It uses timer 2, and that's all good. And I'm going to set this pin, RC0, to be pulse width modulation 3 output. On RC0, tries, but yeah, so 11, this pin is not an input at all, it's an output. So RC0 is pulse width modulation 3, RC2 is CCP1, okay, cool. That all sounds good. Let's save that, generate the config, no warnings, awesome. And I think what we just do, I think it's as simple as if we look at the files that have been generated. So we've got PWM1 and PWM3, and in essence what that actually is, I'm pretty sure, is PWM3 is the real PWM. PWM1 is actually CCP1, and that should be reflected in these registers. Yes, there we go. So we got CCP R1 high, R1 low, because we've got obviously greater than 8-bit control over this. It might be 10-bit, I think. It's just weird that it doesn't have a set. But hey, look, we could try this. Let's run it and see what happens. Now we should get 2 red LEDs coming on. Let's see. Yeah, there we go. 2 reds. Sweet. But I'm going to intentionally set the duty cycle. Well, no, let's do it in our main file. The question is, can we access these from our main? Oops. How do I hate it when you paste code and it doesn't format? Fix code. That's a great menu item. Fix code. Yeah, fix it all. It's all bad. Format? Yeah, there you go. Oof. Why did it do that? Okay. Now, if in my while loop I keep setting these to 0, 0, what does that do? Does that take us down to 1 LED because we're setting the pulse width modulation to 0? Or the duty cycle to 0? And then that'd be a big no. Right. Okay. I did want to see, there were some warnings that we got here before, but can't quite see them now. Okay, so that did not seem to do anything. So let's try it under the, let's try messing with the timer, right? Sorry, PWM3, which is where we should. This is where we get the DCH, DC low values, right? Duty cycle high, duty cycle low. So I think if we take this, and yeah, look at this, this is interesting. Oh. I was looking at this all wrong. Look at this. I was looking at this method here of like load duty value. And I was like, well, I don't want to load it. I want to set it. But this is very poorly worded and ambiguous naming. Because obviously, if I'd taken it 2 seconds to actually look at what this does, it does exactly that. It sets the duty value, right? It takes a 16-bit duty value as an input and writes it to these 2 registers. Oh my goodness. And yeah, it's a 10-bit value. So let's try something here in our main. So obviously, well, that didn't do anything that we wanted it to do. But what if we told this to we got a 10-bit, but let's just assume it's 8-bit for the moment, and let's write a very small value. And what does this do? Surely this changes the brightness. No? How bizarre. Are we even getting to here? I'm not very familiar with this editor, I gotta tell you. A debug main project, maybe that's what we need. There's some errors there that I want to see, but I can't quite get there. Okay, so we're getting to that breakpoint, and there's no LEDs on at the moment, and so if we continue... well, this is interesting. Now we've lost all of our LEDs completely. Nope, now they're back. Oh, they turn off. Do they turn off because the debugger halts the timer, I guess? Because we've got to remember, these aren't... Oh, how do you just set a frickin' breakpoint? Right. Well, hang on, now I've lost one LED. Oh boy. Now I've got it back. Hello, kid. Kid's doing the dance, yes? What's up? You go put some lip balm on? No. Yes. Alright, I don't know what the hell is happening here, but it does seem that when we pause, sometimes we lose something. What's up, kiddo? Huh? Yeah, but then nothing else, okay? Oh, this is really weird. I don't know what's going on here. Okay, well, let's just keep experimenting, shall we? So, that duty cycle did nothing. So let's set a higher duty cycle and see what happens. Right, now, why did we stop there? No, we're just running. Okay. So no LEDs, no red LEDs. Yeah, maybe we should add a delay, bro. I'm sorry, I took my eye off chat for a second there. Okay, so now the board's back on. This is bloody madness. Alright, well that seems to do 5/5 of nothing. Let's try PWM1. What does it do? And then, you know what, we might try just something fancy, because maybe we're just getting fooled by not noticing visually the difference. We'll create a little while loop to walk through it. In fact, you know what, screw it, let's do that right now. For... let's just pass in our integer, and we need just a... Can I use usleep here? I don't know what sleep functions I've got. Do I have sleep? No? Or sleep or a delay function. Let's do find in projects. Looks like we've got a sleep. Sleep but with no value? Okay. Delay. There we go. We got a underscore delay. It looks closer to what I want, but where's that defined? In PIC. Okay. No, to use the macros below, you must have previously. I don't want that. It shouldn't be this hard, folks. But if you think about it, what we're asking this chip to do is a little bit weird. And this is the laziest Google ever. PIC, C, code, sleep. See, I don't think this is talking cross terms. We might need to get the systics and count them ourselves, maybe. Yeah. This is the cool thing about being in yeah, I think that's exactly what the sleep is there. We're going to have to count the systics here, I think. Ooh, what does this do? Oh my goodness, there's the assembly code for it. Let's go back to their example here. This is a 100 millisecond delay apparently. Let's even see if this works, because it looks like they're basically they're basically using some sort of counter, like a systic sort of counter. Let's try that. Let's what's that? Control Shift F for format. Oh, there we go. Oh, this wants us to use this. Okay. Copy and paste in code off the internet. That's what kind of day it is. Okay, well apparently let's see if this actually works. Does this introduce a 100 millisecond delay? And you know what, that's probably too long for us. We probably just want like a 50 milliseconds. We'll do that to 100. Update the math here so we don't look back at this later and just go, huh? So delay 50 milliseconds. Let's just try this. I got no idea if this will work or not. Well, built. And hopefully this cycles through the values of that duty cycle and we just see some variance at all. And if we don't, I'm going to stop, because we really should be doing something else.
A rainbow occurs when the sun's light becomes separated by moisture in the air. The moisture bends the light, thus separating the frequencies.
I can see nothing appreciably different about this. Not a goddamn thing.
This is light interacting with matter.
Even though we're supposedly cycling through this. This is really weird. So, I don't know. But I do know we're wasting time. What we should do is focus on reading these things. Analog. What does it mean? God damn it. What does it mean to set it to analog and output? I don't know. But yeah, it's got like... doesn't make any appreciable effect on the brightness, I don't think. Turn this off. And unless we're... you know, maybe the delay wasn't long enough or is too long. Let's try this again. Maybe the timer is operating too fast. Shouldn't really be it. Okay, let this run. Do one last check of our timers and stuff. Too many bloody files open. PWM. Ah, well, hold up. This calls the initialize, doesn't it? Yep. Okay, well there's something weird going on here. Let's clean this whole thing. What are these errors here? PWM, PW3. Okay, so that built and ran. Let's run it on the board without the debug, because why not? Lights turn on, but there doesn't seem to be any variation in them at all. Nope. Last thing I'm going to check is just the timer config here. Yeah, it's set to be on. But the clock frequency... PLL capable frequency. What happens when you set that? Nothing. Okay. That didn't work. What might we have missed? PLM3 enabled. No. Can't make any sense of this, so we're gonna just say, not today, Josephine. Let's just switch these back to being inputs so we can ignore them. Get rid of our pulse width modulation. Yep, go. Get rid of it. Get rid of that. Get rid of it. Go. You've annoyed me now. Can't make sense of you. Go away. Alright. So, forget the LEDs. Put that in the forget it bucket, and let's do something a bit more productive. So, just to be sure we're in a sane state. Yeah, I agree, Brahim. We need to do more research is needed here. Generate the config successfully, and let's just run it on the board. The PIC we're using here is a PIC 18F26Q10. Chosen for the fact that it was readily available at the moment in the chip shortage, and it has all 8 CLCs on there for handling 4 rotary encoders. That was basically the main thing I needed it for. It's just annoying. Alright, but it's alright. We'll get onto something that we can do here. What's happened here? So let's build and clean. Yeah, and now we need to get rid of our own calls to the setting of the PWM, because that no longer exists. I'm dubious about this whole delay stuff. Let's get you in the go away bucket. And now we're back to just a nice clean old plain project that hopefully we can build and run. Can we build and run? Yeah, we can. Okay. And this should turn on with no LEDs on. If any LEDs turn on here, I'm going to be absolutely lost. Okay, good. Right. Now, let's do what we're supposed to do. It should be, if you can see on the board cam here, it should be this row of rotary encoders, I think, that are configured, or that are are controlled by this. That should be the row of rotary encoders that we're looking to read values from. Let's just double check. Is it this run of 4 here? Yep, it sure is. So the first thing that we've got to do is we've already set up the we've already configured these CLCs to be the right gate configuration. It's the same gate configuration across each of these, just checking all of them look exactly the same. Yep. They all should have the same interrupt configuration, and they do. Wonderful. Now I'm just going to go and generate the code to be sure. And then now we start getting to do something really interesting. So CLC1 is one of the gates connected to one of the rotary encoders, and see how it's got this interrupt service routine here. I'm going to set a breakpoint on that, and then I'm going to run our code. And what we should see is that as soon as I touch one of those encoders, or the particular encoder here that's attached to CLC1, we should hit a breakpoint. Okay, so the program is running. We're not at a breakpoint. Now, let's go twiddle some knobs, see what happens. It's not that one. It's not that one. It's not that one. And it's not that one. I'm starting to think today might not be my day, folks. Yeah, you get that distinct feeling that the world might be against you. Alright, so well, that didn't work. And that's definitely the right and we did hit debug here, didn't we? We didn't do something dumb like not hit debug. But we should have got a call back up in that CLC, so what happened there? And that was CLC 1, which is in... It should have been like off the first rotary encoder. Okay, so we're running again. If we pause, we're sitting in our while loop, which is great. But does anything happen? Not a goddamn thing. Okay, well, what if we... Oh, are you freaking kidding me? We get one breakpoint. Well, that's gonna be fun. I bet if you pay the $1,000 for the better compiler, you don't have that limit. Okay, nope, that's not firing that interrupt either. Okay, so what might we have done wrong here? See, this shows you that I don't ever I never test stuff off stream so that I can jump on the stream and look like I'm an expert. I literally discover these problems along with you folks. Aren't you lucky? Well, screw it, let's just set another one. The breakpoint is at line -1. Oh, it's at line -1. Okay, so we've got no more breakpoints. That's going to be joyous. Let's turn those two off. Let's try and turn this back on. Okay, apparently we now have a breakpoint in CLC 3. No dice. Okay, well that's whew. where do those initialization functions get called? Good question. It's in system initialize, so you know this is a good thing to check. Then system initialize calls all the CLC initializers, so CLC1, that sets all the bits, and then we should be getting a something off that. And just keep checking that I'm actually using the right PIC here. Yeah, it's that PIC. All right. Well, this is fun. What else could we do? So if we're in CLC1, that should actually be the second rotary encoder coming in there. Okay, so, whoops, wrong system. Back here. So let's just check the pin setup. CLC1. We're enabled. It's all the gates set up. Register CLC0. CLC0 in PPS. CLC1 in PPS. Yep. CLC0 input, but this has got that PPS thing. This rings a bell. Maybe not. CLCX, CLC0 in, goes to port RA01, yep. Okay, that all looks right. Hey kiddo, what's up?
How long?
Oh, a little while yet. Why? Okay, well I'm just working through some stuff. Alright, what's going on here? So let's go CLC. We're trying to debug CLC1. And that's taking its input from CLC0 PPS. Yeah, and that looks like that's the only sane option here. CLC0, CLC1. And that we know is connected to, where's U16 is what we're testing. So we know that that's actually the second rotary encoder, the one without a switch. Okay, let's check the pin out. So RA. Well, hold on. RA0. That's right, because it can be routed to any of the CLCs. So RA0 is there. We don't have any pull-up, because that's correct, because they've got external pull-ups on there as well. Oh boy, what a start to the day. Alright, let's take a look at this other project, see how they did it, hey? Yeah, Brian, the CLCs are wonderful. His comment there was that the CLCs compresses a lot of different signals, super powerful and clever. It's my I'm dipping like the tiniest bit of a toe into the FPGA world. You know, I think if I'd had you know, you and I were talking about this. Oh shit! Do you want to save changes? Sure. Having 10 or so PICs to support 40 odd rotary encoders probably should have been just a job for one FPGA, even just a small FPGA to do the same sort of thing, but wasn't quite ready to make that jump. Okay, so now we're in the example file. Let's take a look at how they configure their ports, and I'm gonna have to wrap up shortly, unfortunately, because the kiddo's finished voice chat and calls for the day, so that's what we normally do. So CLC1 takes its input 0 And then 1 and 1 and 1. Straight into that gate. Yep, yep, yep. That's exactly how we have this set up. And then if we look at their pin module, RA0. Oh, sorry, they've got different pins here. What have we done wrong? We got ground signal on this. This is exactly like we did it on the breadboard. Alright, we have a pull up on there. We have a we've got our RC combo just doing a little bit of a filter, cut out the jitter. But anyway you slice it, we should be getting, when that's crossed, it should drop to, if there's no contact, this pin should be high because it's pulled to 3.3. And then if it happens to connect with the ground signal, it's going to pull it down. That's our 10K. It's exactly how we had stuff set up in the test board, the breadboard, when we breadboarded this up. So I'm really at a loss to explain why we don't see anything coming through on these pins. Right, because they're pulled high normally, pulled low when there's contact. The pin numbers make sense, right? Pins 2 and 3. There's the second rotary encoder. But no interrupt fires. Okay, well, let's just try a bit of a Hail Mary here. Let's go back to this project, set as our main. Set as main project. Do you want to save configuration? Nope. Yeah, that's what I was thinking. That might be the next thing we got to do. Yeah. Yeah, that's probably the next step. I'll have to jerry rig a few probe points because unfortunately I didn't put test points in for every rotary encoder because I thought this would work. Silly me. Let's build and clean. Okay, the build was successful. Warnings and stuff, not really. Let's just open the MCC again, generate out our code. Okay, so CLC1. Yeah, I mean I'll rubber duck it so that we're talking through the same thing here, but basically CLC0, so like the A channel of the encoder goes into the first gate. The B channel of the encoder goes into the other 3 gates. And by the combination of it being a 2-input D flip-flop and the way we've got these gates set up, it should be such that we get an interrupt on CLC1 when we're turning one direction, and an interrupt on CLC2 when we're turning the other direction, right? Because we invert the gates that we've got configured on there. That's 2 and 3. That's 3 and 2. 4 and 5. 5 and 4. 6 and 7. 7 and 6. What is going on here? What have I missed? Let's just generate out the code. Maybe we, I don't know. Clutching at straws here. Let's try it. Just trying to think, can I get an oscilloscope probe on this easily? Okay, well I just did a very quick test that you can probably see my hands are on the board, and I do actually see a good square wave coming out of one of the encoders. So, and I use the same configuration everywhere, so so I think we're good. What's this doing? 5/5 to nothing. Hello? Anything? No, that's now frozen up. No, is this thing totally dead? Oh, great. Thank you, Brian. I appreciate the compliment. Almost as much as oh no, it's back. I was just about to give it the for goodness sake. What is this thing doing? Give it the force quit with a vengeance. Alright, let's go back, generate the code, try and get ourselves in a sane mode of operating here. Alright, so we're back. Close out all these files. Headers here. Sorry, the project's here. Let's clean and build. Okay, cleaned and built. Now, going into the source files, we're going to try and do an interrupt. Trying to set a breakpoint on the interrupt of ISR, the ISR for CLC1. Let's debug. Okay, we're running. Let's try toning some encoders. No, no such luck. Alright, well, I think it's time to take a break, because this is not getting us anywhere. It does seem odd that, nothing we tried to do with this chip this morning has worked, other than writing code to it. So, that kind of gives you the sense that there's something deeper wrong here. Whether it's the, I don't know, maybe something as basic as clocking or something else. It's just not doing what we're expecting it to do. So what could that be? What could it be doing, or what could be wrong? So we've got CLCs, all those are enabled. In module. And that all looks fine. And then the package is quite right though. I think we're actually using the Anything SOIC 28? I mean, it's either that or it's the TSOP, but that shouldn't make a difference. Because the pin numbers are all the same. Is there anything left to try here? Anything left? Just feels like there's something fundamentally wrong that we've forgotten to do. Let's look at that timer. Let's get rid of that, just in case. So let's generate this config out. And we'll go to the files, projects. The other thing I thought we might turn off that is the only thing that's different from how I've done this in the past is we just disable the I2C opening. And let's just try this. This is it. Last try. Hey Xena, they should be all there in like the video section of the channel because I have it set to auto record. I think it keeps a history for I'm not sure how long, but if there's a history, that's where they'll be. That didn't work. Try again. It's really annoying that you have to keep cleaning and debugging or cleaning the build each time you change that configuration. It doesn't do a good job of managing its code dependencies. Alright, last thing to try, then we're going to take a break, go do some learning, see if we can figure out what we've done wrong here. It's got to be something simple, has to be, right? We're a bunch of smart people all trying to do this. Alright, we're running. Are we debugging? Yes, okay. Just for fun, I tried twiddling every knob possible. Blue link warning to check. Where was that? Yeah, I'm really not sure. But all I know for sure is this ain't working. So I think it's time to take a break. LC2 enabled. Interrupt on the negative disabled. Interrupt on the positive enabled. Just never seeing this interrupt service routine fire. Okay, well folks, I'm beat. I'm beat. I don't know what's wrong with this bloody thing. Other than I'm just gonna do something bizarre and try a completely different clock configuration because why not? What could possibly go wrong? What have we missed? What have we missed in here? Like I said, it just feels like there's something fundamental to all of this. Like interrupts are just not working at all. Oh my god. What does this say? Please remember to enable the peripheral and global interrupts in your code. Oh shit. Are you serious? Enable global interrupts. Enable peripheral interrupts. Oh my god, I'm gonna cry. I'm gonna cry if this is what it is. And I already know it is, I can feel it. Why would you not turn the fucking interrupts on automatically? You all know this is what it is, right? Okay, are we running? No, not yet. Programming, running. Okay, here we go. I'm gonna touch the knobs. I bet this gets it to work. It's not that one. Ah, yes! Okay, well, I'm gonna wrap the stream up here anyway, because kids, you know, like I said, you know the rules. Kids not streaming or playing games, I'm not streaming, so I'm gonna wrap it up there. But oh my god, I can't believe that it took us all this damn time, all because we missed this one little hilariously lacking warning here. Please remember to enable global interrupts. Listen, if you've let me tick this all on and you generated that config for me, really shouldn't have had to do that. But I think I get why, because I don't think... I know MCC does generate the main for you, so no excuse. Just really quickly, I wonder if this fixes up the 10 minutes, kiddo, okay? Just out of interest, like I wonder if this fixes the LEDs. So let's do pulse width modulation, timer 2. Let's set RC0 to be pulse width modulation 3, timer's 50. We need to add timer 2. Timer 2 enabled. Enable timer 2. Set that to free oscillator 4. And then we will turn. This is not an input. Okay. So if we generate this, do we get one LED on? Yep, okay. Clean it and build it. Yes, I totally agree with you, the white 1989. They should just be uncommented out of the box. Why would you have them... Why would you put it there and comment it out? And like, if there's other code in it that's enabling stuff with an interrupt and the interrupts aren't enabled, then it should scream. It should be like, you know, crash, error, warning. No, you're an idiot. You didn't realize that you have to manually turn on the things and shit. So we got one LED on. Great. I want to say it looks a little less bright. Let's go to our code here. Projects. PWM3. Where's that routine? Load duty value. We're going to go into our main. And right before we go into the while. Sorry, I got a big freight train going by outside me here. And just set a duty value like that. Let's just see what this does for starters. I just want to see if we can get like a you know, an obvious difference between the duty cycle values. That's building, uploading. Oh man. Oh man. Man. What else was in that main file? See, why do you even have function here that's like interrupt global interrupts enable, interrupt global interrupts disable? If using interrupts in the PIC 18 high and low, you need to enable the global high and global low, right? If using interrupts in PIC mid-range compatibility mode, you need to enable the, well, I don't know. odd. We need to understand that. I can't discern a difference there. Alright, let's just try an extremely small value. It would seem to blink then. But I think that's just because the chip's getting programmed. Okay, so now it's off. It looks exactly the frickin' same to me. Okay, well, so the PWM stuff is still not working, but we can go back and work that out later. I think we've reached the zenith of our embedded coding abilities for today. So I'm going to do a bit of research offline to work out what do we got to do to get these LEDs controllable. And we'll be back tomorrow, probably later tomorrow, because Kid and I are going out for a hotel staycation for the night tonight, which is always a bit of fun. And I just can't let this go. What the is wrong with this? So CCP1 uses timer 2. What's using timer 3? Timer 2 is there. Well, that's interesting that timer... They've got timer 3. And it's configured quite differently. Enable timer. I've got this sneaking suspicion that you needed 2 different timers for this CCP to work. Why does that sound familiar? Because what else is using any timers here? The ADC maybe? No, it's got its own clock source. Has they got an info here? It's 1-to-1 CCP4. And how do they have this timer set up? Its timer period is 32 microseconds. They've got I2C peripheral, timer 3, enable synchronization, and enable timer input. Oh, that's just their that's their finite state machine. That's right, I remember now. Well, let's just check our values here. 32 microseconds, 32 kilohertz. Do we have something similar? And then I'm really gonna go. Told the kid 10 minutes and I should stick to it. I think I need a donut. Nope, don't save that. Okay, now go to this. Now, well, that's a different value there. They have 32. $32 US. And that's now reflected the same settings there. I don't know if that would make any difference at all. Roll over. Alright, last check, last thing. Does this change the brightness at all? No, it really doesn't look like it. That looks like the same brightness it's always been. Oh, that's the wrong main file. And are we thinking about this right? Yep, pretty sure. Hang on. So, this is the breadboard prototype of this. Or at least it was my prototype of how to do the rotary encoders with a PIC. And this, we definitely use LEDs with a with the CCP successfully. Yeah. God, I wish I could find the code for this. I'm gonna have to hunt it down. I'm gonna hunt that down. Okay, folks, I'm gonna go. It's time for me to go be a dad. Thank you all for hanging out, and thank you for, as always, putting up with my inane ability to bang my head against a wall and get frustrated with stuff. But hey, we got somewhere. We got the interrupts working for the rotary encoders. That allows that chip to then act upon the rotary encoders moving. And then we can do all sorts of fun stuff like track, you know, where it's moved, how much the value has changed. We'll be reporting that out through an I2C bus. So we've got lots and lots of code to write, which we will do together probably sometime tomorrow. But for now, I'm out of here. I'm gonna go have a donut or something equally terrible. And the camera's about to go flat anyway, so I'll see you later.